Welcome everyone. Tonight we'll present the final results of the AI for Turtles challenge. Over the last 10 weeks we worked very hard with multiple teams to come up with some very cool solutions for turtle identification. Before we start, I really like to thank Dan and Kai for starting this challenge with us from the STCB, that is the Sea Turtle Conservation Bonaire. Very cool organization which cares for the turtles on Bonaire and came up with a very large, very cool data set for us to try some really innovative AI on. So today we have we can show you the results of the last 10 weeks, and I'm very eager to get started with you all. I see some new people, so I will also give a short introduction about Fruitpunch AI, just for you guys to understand who we are and what we do and why we do this. Today you will hear from me. I'll give a short introduction. Then the first team that's up for presenting is the face detection and segmentation team. Second team will talk about feature extraction and the actual identification of turtles. And the last team will talk about application building. In the end, I have a couple of minutes left for some final words for you, Kai and Dan. And Saka and I will also give our thanks in the end. During the presentation, if you have any questions, you can click on the raise your hand button in the bottom of your screen. That's this one. You can immediately, or you can ask a question once the speaker gives you the turn. If you prefer, you can also put your question in chat, and then I will ask it once the Q&A starts. So that's also possible. So who are we? Well, we are Fruitpunch AI, the global AI for good community. And we started this community because we believe that to solve humanity's greatest challenges, we need to educate engineers at scale with an ethical and sustainable mindset. How do we do this? We do this by organizing AI for good challenges. And we define AI for good by linking all our challenges to the sustainable development goals. This one is from the top of my head with the Sustainable Development Goal 16, life below water. And it's one of in our streak of wildlife challenges. For this challenge, we focus a lot on computer vision and segmentation. That's also what you will hear about from all the teams. Apart from getting your hands dirty with some real world data, our challenges are also a great way to learn in a very cool peer-to-peer manner. And you can also get mentored by our experienced mentors. So why do we actually need turtle identification? So we came up with this problem, or at least SCCB Dan came to us with this problem of re-identifying turtles. So they use this in order to do population monitoring. Every year they go out by a boat and dive to catch turtles, to weigh them, measure them, but also to take pictures of the head to see if they captured this turtle in previous years as well. The way they do re-identification right now is by tagging the turtles in their flippers. Is that wings, flippers? Is that the correct term? But this tagging of turtles can be very intrusive and can cause some change in behavior by the turtles. So ideally, we should find a less intrusive way of re-identifying the turtles, and this is where AI comes in, because using computer vision, as you all might already know, your iPhone or your smartphone already does this pretty well. If you try to open your phone recognizes that you are the only person with this digital fingerprint of your face. And this likewise techniques did we try to use in this challenge to re-identify turtles. So basically just face recognition for these sea creatures. The goals of our challenge, our main goal was to create turtle recognition software to identify individual turtles in order to do population monitoring. But we broke up this problem into a couple of sub-goals. We started off this challenge with researching various methods for recognition, as well as for face detection and segmentation. Then we went into actually building and training models for object detection and segmentation. You will hear in the first presentation, you will hear a lot about this. And we needed this to be able to detect if there was an actual turtle image in the picture, as well as to cut it out so that the feature extraction models would have to deal with less noise in the image. Then the third goal, that's where the second presentation will be about, was experimenting with recognition models. So a lot of deep learning or neural networks on top of more classical feature extraction techniques, older computer vision techniques. You will hear a lot about it from the feature extraction team. And then finally, we also needed to be able to give all these advanced AI models to STCB and make it possible for them to work with it as well. As you can see, one of the goals was to run it locally. That was one of the main hurdles in the end. We came up with a very nice solution, which makes it possible to run on a laptop. But just a quick spoiler is that you do need an internet connection. But yeah, you will hear all about that during the application presentation. Yeah, as already briefly discussed, the face detection team was building object detection and segmentation models to focus on the turtle's face. That's the first presentation. Then we had the feature extraction, mainly focusing on extracting important features from the turtle face that we can compare with other features from other turtle faces so we can make a match. And finally, the software development side where we make a user interface. So yeah, over the last 10 weeks, we worked with 3 groups, 21 very enthusiastic AI engineers I had the pleasure of working with. And together, collaboratively, we put in over 1,600 hours of engineering work. So definitely already something we can be proud of. But yeah, not to take up too much of the time, I would like to introduce the first team, the face detection team. And I believe I can give the floor to Hamza or Rob.
Yeah, let's try if you can hear me now. So everything's good. You can see my screen now.
Yes.
Yeah. So this is the final presentation for the detection team. We're a team of 7 members, if I'm correct. This is the full list. Hamza, by the way, if you want to interrupt me with any slide, feel free, or anyone else from the team or from the other teams, feel free. I think most of this has already been presented in the halfway presentation, so I think we can be rather quick. So first of all, why do you want detection? Well, the first reason is that if we get a picture of a turtle, there's turtle, but there's also different stuff in the picture. And for the re-identification picture, this different stuff is confusing. So cutting out basically the turtle head itself and only sending that to the re-identification to the feature team, that will basically make things more simple for them and thereby improve the performance. Basically, I want to detect the turtle to make it more simple for the next step. And so what we do is input, we use this picture where presumably there's a turtle. So first we run a detector, and the detector gives us a box around the head if there is a turtle. If there's not a turtle, there's no box, and then we don't do anything, of course. Then we run a segmentation model that, as you see here in the center, it finds within this detection box, it finds the face of the turtle, so not the neck, but only the face, and not the other pixels in the square, because the turtle head is not square, of course. And then we added, since the halfway presentation, Hamza made a nice component where we estimate the rotation of the head, so that we re-rotate the head. Let me zoom in onto that. At the right, we rotate the head so that it's always horizontally aligned. Why is that necessary? Well, it's not necessary, but it removes variation that does not need to be dealt with in the re-identification team for the feature team. Basically, the picture that we send to them are now always the same size, basically, and the same rotation. So every turtle is looking either to the right or to the left. And we also estimate the face side, so whether it's looking to the right or to the left. So this was initially supposed to be entered by the person that uploads the picture into the system, but it can now be done automatically. So that's a nice side effect. So I think that's a great addition to the whole system. Quick update on the data set. So we have 6,000 images. Recently, of course, Dan uploaded also some older images. So I think we started with 4,000 something. Now we have almost 6,000. Almost half left, half right images. And the distribution looks like this. So as you see in the beginning, 2003, the images captured was only 150. And then I think the peak was in 2016 with 500. And it's a bit varying over time. Then very quickly, what is important is, of course, for re-identification is that we need examples of turtles in the past and in the future, not in the future, but at a different time. So we need at least 2 views of the same turtle, of course, otherwise we can never train or test an identification system. This plot shows with 1 where the peak of the data is that there's only one occurrence of the turtle, and 2 means there's a full double occurrence. So there's both a left and right side of 2 different moments in time for that turtle. So you can see there's 260 turtles that appear twice, and there's 33 turtles that appear 3 times even, and there's only 6 that appear 4 times, and there's even 1 now that appears 5 times, so that's quite cool. Just to give you an idea of the data. Of course, gathering data for AI systems is typically the most challenging task. You can see that if you need, for example, 5 occurrences, that we'd have to do a lot of work in the field to get more data for that point, because you have to be lucky with capturing that exact turtle. Then we expected the data set and we found some issues. Typically, this is a process that takes some time. I think in hindsight, I think a lesson, at least from my side, would be that we should have started this a bit earlier in the process and a bit more extensive. So last week, I even had a call with Dan to discuss some issues about pictures that appeared multiple times with the same ID, and then we found out that they were actually not the same ID. So that also introduced some noise. We fixed that, so that's great. So what did we see? Some pictures were rotated, as you can see, upside down or 90 degrees rotated. There were some uploading went wrong, so some images were corrupt, and some images were of low resolution. I think most of the issues there were fixed. So now the data set that we have is very usable. Then we trained an object detector. We used for that the YOLO, which is you only look once. It's a funny name for an object detector. So it's a neural network that basically processes the picture at the bottom, and then of course looks in the picture to find certain features and does it at different layers. So in the lower layers it finds like corners and edges and different variations of colors. And in the higher layers it combines these things into finding in the end the turtle head. We won't go into the detail because it's not important for this presentation, I think. But in order to train that model, and about 1,000 images were manually labeled. These were split in a train and a test set. And then this object detector was trained for about 4 hours on a GPU. And then the performance we got was close to ideal, as you can see in the right top. So this is the recall precision curve, where recall means the amount of correct turtles you detect, and precision is each of the detections that your system outputs, are they correct or not. So if both are 1, then you detect everything and all detections are good. So you can see that all detections is good. It is a little bit overtrained though, and that's actually nice in this sense, because typically all pictures that we give to the system have a turtle, right? It's never a picture of a television or I don't know, a cat. So that's great. But if we want to use this in the field, like for underwater pictures, that will be a slight addition, then the performance will be not good enough probably. Then we go to segmentation. So we found this box of the turtle, then we segment it. Instead of training a complete segmentation network, we opted for using a foundation model, and a foundation model is basically an AI model that has been trained with a lot of data. And that's this year the first foundation model that was actually launched, and that was the SAM, Segment Anything model by Facebook, or now known as Meta. And basically it is trained with so much data with so many classes that it basically segments anything. So you give it a box and then it segments the most probable object in that box. In this case, you see that it actually works quite well. So I think in around almost 99% of the pictures, the segmentation is quite good. Sometimes it picks, for example, the leg of the person behind the turtle instead of the turtle, but that occurs only very rarely. The drawback is that it's relatively hard to compute, but for now, this wasn't really a problem. Another optimization would be to improve the speed of this segmentation network, or train a specific segmentation network that does not know about every object, but about turtle heads only. But we didn't get that far in this project. So segmentation results here, just to give an idea, I think it's robust to the variation of the rotation of the turtle, which is nice. And it detects the turtle head quite nicely. So then the most important update that we added in the last months is, an angle regression network. So basically it tries to rotate the image and then tries to find the rotation angle in which the turtle is horizontally rotated. So in this case, for example, we would estimate that it's roughly 90 degrees. And then we can rotate the image 90 degrees, and then basically you see that the turtle is always looking to the left. And the nice thing is, if we have 2 images of the same turtle of different years, and one is looking to the top, for example, the other to the bottom, is that all the patches are almost 180 degrees rotated. So if you align these rotations, then that rotation is almost 0, which makes the comparison of these 2 turtle heads more simple. So that will hopefully improve the re-identification system component. Hamza was so nice to upload this also to Hugging Face, so you can actually try this online in a live demo if you click this link. And then the last part of the presentation, and then we move to the feature team, where I think the most interesting and challenging part of at least the second half of the project has been going on. We made a table, an Excel file, a spreadsheet, where we put all the labels of all the turtles, and then with how many times they appeared. So you can actually use this data set, this structure, this Excel file, data set, whatever you want to call it, to look up the data and to find which turtles appear more than once and things like that. And this has also been used as input to create the training set for the re-identification system. I think basically that's where this presentation stops. The last slide for the detection part, I think, is basically the next steps. So I think the next steps to improve, if we have a continuation of this project or we continue in any other way, it's of course segmentation, which is rather expensive at this moment. I think we could train a simple segmentation network, probably in combination with a detector that is trained on turtle heads only, that can only segment turtle heads, but that's sufficient. That will be rather fast. But we didn't get to that in this project. And then the second step, if we want to go also have this operational underwater images, then we also need to train the detection system, of course. But underwater images, they should be added. I think both steps are not like super challenging. They're a lot of work, but it's work that is easily done. There's not really a research or unknown component in that, so that's good to know.
Hello everyone. I will be presenting the part of the feature extraction where we have worked to create the AI model that does the actual matching of the turtles between the query turtle and the turtles in the data set. So these are the people that have worked in this team throughout the months that we have done this challenge. My name is Davide, and a lot of people have put many hours of work into this. So for this team, the objective is to identify the turtle. What we want is a system that, given one turtle image that we are going to call the query image, we can fit this into one AI model, and the AI model has to answer the question, who is this turtle, given the pre-existing information on some other turtles that have been included in the data set. How this works generally is that the AI model goes to reference the reference set and tries to find the closest match, giving then a set of, we decided, 5 turtles that are the top matches and the confidence score that is associated with each of the matches. Now, the tricky part is what goes on inside the AI model, because there are many different ways in the literature that this can be done. So for this challenge, we focused on 3 different kinds of approaches. These are the metric learning, light blue, and low FDR. Metric learning is a bit more classic approach, whereas light blue and low FDR are more modern approaches. And towards the end, we found that light blue is the best performing models, and this has been also chosen as the model to be included in the final application. Whereas the other 2, we have more like research insights to share. So for the next few slides, I will just briefly go into the metric learning and low FTR to show you how they work, and then focus a bit more on the light blue. So metric learning basically is a system that tries to learn how the distance between images. It tries to, given a query image, to create an embedding of this image in the feature space and to match it with other turtles. How this is done is usually with the existence of positive examples, and this means, in this case, turtles that represent images that represent the same turtle, and negative examples, and these are turtles that are not the same. And what the metric learning algorithms do is that in the high dimensional feature space, they try to pull closer the turtles that should represent the same thing while pushing away the representations of the turtles that are not the same. There are various ways how to this in the literature, and over the months we experimented with a few of these. So we used mostly the PyTorch metric learning library and the FICE library, which is a library to do fast computation of similarity from Facebook. And unfortunately, with this kind of approach, we didn't get very far. This might be due to the fact that we saw that the models were quickly overfitting, and this was probably due to the small number of what we're calling hard pairs, which is not good for this specific kind of metric learning approach. Hard pairs means pairs of turtles that actually are the same. And if you go back to the presentation that Rob just did, the number of actual turtles that appear more than 2 times, so that we can use them for training and for test, is very, very small. Then the metric learning approaches in general are notoriously hard to train, and we also needed to use a lower resolution for how the models work. However, the inference is very fast in this case, and FICE in this case, it was actually working on CPU on Colab, but yeah, it wasn't very, very well performing. Then low FTR is a local feature matching with transformers. As you can guess from the name, it uses the transformers, one of the best models of the last few years. And these models in the literature are known for performing very well in feature matching. And what they try to do is that they find some key points between the images, 2 different images, and they try to match these key points with a very magical algorithm. The issue with low FTR is that the model that they use is very big, and the algorithm is very expensive computationally. So by using the original low FTR, the team was able to achieve pretty good performance, especially when looking at accuracy at 3 and at 5. However, as you can see, the total experiment time was 5.5 days, which means for 100 images, it took 5 days to compute this on a GPU that was remotely deployed. They tried to reduce the number of key points and using a smaller model, and this is the coarse low FTR, but they did not perform as well, and even took longer time, it seems. So yeah, this was also not feasible for the final use case. And here we are at the winner of the 3 approaches, which is light blue. Light blue is a 3-step approach where we have a first part that is the extraction of features and key points using any kind of algorithm. Then the actual light blue, which is a matcher of key points between one image, one query, and the images in the data set. And then the team actually came up with a very interesting and actually novel solution that also improves on the original paper for the matching of the turtles. So among the various algorithms, the team in the end decided to go with SIFT, which is a very classic computer vision algorithm for finding key points in images. And the way it works, very briefly, is to apply a Gaussian blur, a transformation on the image, and then by doing this many times, you see where the differences are the biggest, and those are generally the key points. The thing is that because this is not a supervised way of finding key points, usually this tends to find also points that are not relevant. As you can see here, there are key points in the knee of the person or in the background. So that's where light blue comes into place to remove the points that are not useful and to find those that are actually useful. And of course, match them in other images. So light blue is an improvement on an already existing method that's called super glue, and it makes it basically faster and better. What this does basically is given two sets of key points extracted from two images, it computes which points have a match. For each of the points, basically you have a confidence score that indicates how likely it is that that point is a match. And by using a threshold, you can count the number of points per image that match with the query. And of course, if you do this for all the images in the reference set, you can take the image that has the highest number of points that match as the number one match. However, this didn't seem to work sufficiently well, and that's where the team came up with this solution for matching turtles that improves on just simply counting the number of points that match above the threshold. How this works is that, as you remember, I said that for each of the key points, there is a confidence score associated. So given a set of key points, you can compute the distribution of the confidence scores associated with that image. So between the query image and the image in the reference set. By doing this through between all the images in the reference set, you will have a number of distributions, and these are the ones that are plotted here. As you can see, the red ones are the distributions that correspond to images that match with that have found a match, that a correct match, whereas the other ones correspond to images that are not matching. So what this means is that the two distributions have very distinct shapes, and this information can be used for developing a method to find which one is the best matching turtle. So the idea was to first compute mean distribution of images that do not match, and then compute basically the distance between the distribution that they find and the null, what they are calling the null distribution. If you recall from this picture here, the matching images will be further away from the null distribution, whereas images that don't match will be closer to the null distribution. This is done using the Wasserstein distance, which is a classic way of computing distances between distributions. And by doing this, it is possible to see how using this Wasserstein distance, the system is able to correctly identify the turtles that are the same and the turtles that are different. This plot here is done on a smaller subset, and you can see that there is a clear distinction between where the points are located in terms of Wasserstein distance. You may notice that there are a few points here that have a low score of Wasserstein distribution, but the team actually went and checked these points one by one, and they saw that these were images that had some artifacts. For example, the rotation was wrong, they were upside down, or the turtles were not very clear. Once we have a system for matching the turtles, the next step is to be able to identify when a turtle is new, which means when a turtle is not existing in the set that we already have. And the way this is done is kind of similar to what I have explained before. Again, you can see that turtles that have a match tend to have a distribution of the Wasserstein scores that is very spread out, whereas the turtles that don't have a match, so it means they are new, they tend to have a distribution of Wasserstein scores that is with the orange shape. So by applying basically a threshold on these two distributions, you can compute the probability. Sorry, you can compute the probability here that a turtle is new. So there will be a demo later from the application team, but just to show what the algorithm does, given an image, it is able to compute 5 possible matches and associate and flag whether the turtle is new and associate a confidence score in terms of p-value. There was also a very last-minute update from the team today, and this is a case where the algorithm was able to pick up a turtle that had been mislabeled in the data set, and because of the way the algorithm works, it had found a match, and this was flagged as a wrong match, but by looking at the actual image, you can see that these are actually the same turtle. So by using the light blue algorithm, it was possible also to find a case where the label was wrong and corrected. So as a summary, we have used 3 different kinds of approaches for matching the turtles, and light blue was by all means the best performing in terms of accuracy, novelty detection, and inference time. And for the inference time, it does need a GPU, which is used for the light blue matching algorithm. But other than that, the performance is worth the use of a GPU, even on a remote server. So for future improvements, the first thing, as was also pointed out by Rob, is to keep the human in the loop and to assess the quality of the data, because this can really affect the quality also of the models. So by constantly revising and improving the quality of the data, we can also obtain better matching algorithms. The next step would be to try to optimize the models for CPU to allow the execution on the edge, or if this is not considered strictly necessary, maybe to find a solution where the models are deployed, for example, on a serverless solution somewhere. Then one thing that is missing right now from the algorithms is the ability to add a new turtle, this is a feature that kind of goes into also the application team. But for light blue, what this means is that there is no need to retrain the entire model every time a new turtle is detected by the users. The embeddings that are the key points that are computed by light blue can simply be stored and be used as further reference for when another turtle is then queried, which is the final point, which is once we have added new turtles to the reference set, we also want to test the ability of the model to re-identify turtles that were not used during training. So turtles that the AI model had never seen before during the training phase. So that said, I think we all did a good job, and especially the light blue team, and thank you for the attention.
Thank you, David. Very good presentation. Looks very nice, and sweet that you also were able to actually go back into the dataset and find one mislabeled image. Like that does show tribute to how well the model actually works. So that's impressive. Good work. All right, then we have one last presentation from the application team, who will also be doing a short demo of how actually all these algorithms, how you can actually deploy all these algorithms and use them on your own data. So there were, for the application team, also a couple of hurdles which will also be discussed. And just I also wanted to say this before, Dan and Kai, I will also schedule a meeting with you guys to do a kind of handover where we're gonna basically walk you guys through everything and how to actually use it and how it works. But before I schedule it with you, I would like to give the word to Alex or Barbara.
Yeah, hi. I'll
Hey.
start the presentation and then Alex will come later. Yes, so welcome everyone. This was the application team and it was comprised of me, Alex, Sonny, and Deb. So our goal was to build an easy to use graphical user interface that could be run locally on someone's computer. And from the user requirements that were gathered, we had developed a scope where we divided things into top priorities, should haves, and nice haves. So for the front end part of the application, they wanted somewhere they can easily upload an image and then use those images to detect a turtle, export those results as a CSV file, and then also be able to retrain the model. Then the should haves were the user interface was for model, it could be used for model fine tuning, and then there'd be a turtle database for and management for the user interface. And then nice to have was an offline and mobile application. So over the course of the 10 weeks, we managed to at least do most of the front end, which we ended up with a next using Next.js with Ant Design, and we were able to get it at least running on mock data, and where a user can be able to upload a folder that has the images of the turtle, and then there was a form there where they'll be able to add the new details of a new turtle, and then it also has the turtle database management user interface. Then the backend progress where we faced a bit of hurdles was where we were trying to integrate the face detection code and the feature extraction code. So one of the hurdles we were facing was trying to run the inference model locally without a GPU, and yeah, that caused a lot of time being taken. And also in the beginning, we were trying to use the SILnet application and then kind of configure it to the Turtle application. But because of dependency problems, we had to now restart everything from scratch. Yeah. So right now, I'll just show how the front end currently looks. Can you see the screen?
Yes.
Yeah, so this is what we were able to come in regarding the front end and Next.js, where they'd asked if, depending on the models that they wanted to use from the feature extraction team, they could either choose light glue, the SIFT model, or the feature relation model. Sorry. Yeah, and they can be able to get a folder and then drag it here. And then on the side would be where now the images would come up. I have to share my whole screen. So say this is a picture. This is a folder with the turtle files. So you just simply drag it here, and then it should pick up the images from there. Then when you click match, it would run one of the models that was chosen, and then based off the JSON output that was shared by Marcus from the feature extraction team, we were able to come up with this, where it shows the similar matches that were found with the turtle ID and the confidence level. Then if the new turtle came as false, then that means it was already in the system and it would say matches found and then still show around 5 similar matches. Then if you click on one of them, it's apologies for the CSS, but it would show now the other details of the turtle. So from now the species, new, recap the tail, apparent sex, weight, observation, and all those. Yeah. Then if you still wanted to add a new turtle to the database, yeah. So this is what the form would end up looking like based off the one that they'd given us from the Kobo toolbox, where it has the date when you captured the turtle, the name, the participant, the location, turtle ID, and then a place where you can also upload the different pictures that you took from the different sides of a turtle. Yeah. Yes, then you'd be able to submit. Then if you want to see the turtle database and management user interface, this is how it would end up looking. Then once again, when you click on one of them, it would show the turtle ID with its details. And then hopefully when in the future, for the future challenges, they can be able to now complete it and be able to download this list as a CSV file or search for the turtle. Or if they still wanted to go back and add a new turtle, they'll be able to do so. Yeah. So, yes. So I'll hand it over now to Alex to continue with the conclusions.
So where are we at now? Can you see my screen? I guess so. So I have only 2 slides, just to call out two main things. I think as I've been building softwares for 20 years now, and it's one of the first time I feel so frustrated to not have been able to reach the end. So as you have seen, Barbara spent a lot of time, and I want to call out that Barbara did a lot of amazing work just to mock an application that could be potentially used. The main issue is that we never managed to connect the application to the models and to whatever is behind the scene. And there are several reasons for that. And I think it's important for us as a team to remember that for the next projects, because for us it was a bit frustrating in the end. But also I think there is those two worlds, machine learning and software engineering, are still two separated worlds. And I think if both sides of the world can keep those two ideas in the back of their head, that would probably help improving the final results. So what we've done in the last 4 or 5 days is basically we step back and say, instead of trying to solve a lot of things like the total database and doing a nice UI, we focused again on the essential promise of the challenge, which was basically as an STCB. I said employee, but I don't know, someone who works with taking pictures of turtles. I basically need to just upload my pictures and get the predictions we are looking for. So this is really the essence of what we are trying to do, and hopefully we have a solution I'm going to show you in a few minutes. Behind the scene, we need to have the productive models, and I think that's a key thing for the whole machine learning teams, is because aggregating all the amazing things actually that all the teams are building is something which is required necessarily at the end. The thing is that it comes really late in the process, and I think maybe if we start earlier by working all together in the thing, even if it's simple, if it's not performing well, but designing the things all together, I think will definitely help having a result just way before. Clean up directory structures. That I realize that we have a gigantic Google Drive. We grows, and it's really hard to find our ways in there. But I think that's the nature of how you guys work mainly. What's missing in the story is how do we retrain the models. I think someone mentioned, David mentioned how this is going to work, but we don't have a story to tell to STCB in the future how they're going to do that. Someone from us will need to be doing that, and that's also something probably we need to think about at one point. And the bigger issue is the infrastructure, and I think I have a slide for that. So it's just I'm not going to spend too much time on that. It's basically I explored a lot of paths and a lot of tracks. I played with my own Python web server, trying to call them the models and trying random.com, deploying on AWS. etc. All of that is super complicated, especially for an organization which doesn't have the budget to maintain this infrastructure. So when you mentioned, I think it's David again, sorry for that, that requires GPU, each time I heard requires GPU means that someone has to pay for a machine somewhere. And that needs to be considered when we design those solutions. So yes, it's great, we can do crazy things, but when we need to go to production, we have to have that in mind somewhere. Someone will have to pay for those things. So we also tried the full local approach with potentially a Docker image, but that's also means that we're going to have to give that to the STCB people who have probably no IT people who can maintain those machines. So this is probably a no-go neither. And they don't have the computer power in-house, I'm sure. So in the end, what we've managed to do as a group in the last 4 days is to come up with a simple collab solution, Google Collab solution. Very limited, very simple, but at least they can achieve the goal, which is basically identifying the total. So this is now the part of my demo. My story starts. I'm a photographer. I took pictures of several turtles, actually 4 turtles. This is my USB stick, so I just create a folder, just fake USB stick. Just plug it to my computer. I have those 4 pictures. I'm going to show you the pictures. Basically, random pictures from the datasets or the database. So these are the pictures of the day. I named them just to be able rename them just to be able to identify who is what, because if I could have called them picture 1, 2, 3, 4, it doesn't matter, just for me to know what's going on. So I have my USB stick plugged, and what I need to do is basically go to the Google Drive. So we've prepared or cleaned up a Google Drive where there is still a lot of things in there, but the only 2 things you need to know about is the predict folder and the notebook, which is there. So the story continues in the predict folder, which is empty at the moment. So the only thing I'm going to do is take those 4 pictures and upload them in the predict folder. Just wait a little bit for all the pictures to be uploaded. I have a good internet connection, so it should be fast. As you can see, the images are 4 megabytes, so it's really the images coming from a camera. No problem with that. And then I go back to the notebook, which I'm going to open. And the only thing I need to do is to hit the runtime run all button. Then you need to wait. That's a fact. So first of all, the machine is going to start, and then this thing is going to run. The notebook is going to ask you to connect to Google Drive. That's probably the only last step which is required. So again, as Dan or Kaj, I just need to connect to the Google Drive with my account. So this is me. Just need to say, OK, yes, hello, everything. And then things are going to run. It takes about 5 minutes for the 4 pictures. So we're not going to wait for the 5 minutes. I prepared the result here. I'm just going to expand here. So what will happen is basically this thing is gonna run. The first step is to pre-process the images. So this takes about 50 seconds. And then for each image in the folder, it's gonna create some kind of a report like this. We have 4 images, and there are 4 reports. I'm gonna start by the last one. This is the new .jpeg. So JPEG, just as the name explains it, it's a new total that has never been seen before, really brand new. So as you can see, it's flagged as new true, and the confidence is 0.95. There are some results, but they are far off. So this is potentially really a new total. There are 2, the A and B are recaptured, one left and right. As you can see, there is no need for me to say this is the left, this is the right. So this is what the team explained before. They are able to recognize if it's left or right. And as you can see, it is pretty confident that this total is this one. Actually, obviously, it's the same image, so it's probably easy. You would tell me. But basically, it works. So basically, I have it finds the 2 corresponding totals. And there is a third example where this is recaptured, but it found the same image, so with a lower confidence, but it's really the same total. The capture C is the 1350 52, and it found it in the previous years. So it really is really able to re-identify the same turtle adequately. So Kaj and Dan, sorry, you can definitely, starting from now, start using the same process to basically try to re-identify turtles. And as you can see, it's really just a drag and drop and one button to press, and just wait a little bit and you have a result. Basically, that's the end of the presentation.
All right, very nice. Thank you, Alex, for the nice demo. Dan, Kai, do you have any questions so far? We will, of course, have a separate meeting where we'll go over all of this in a bit slower and a bit more detail. But maybe you've already seen something you want to ask.
Not on my side. I think it would be really awesome to go over this in a little bit more detail in another time. But I'm super impressed. It looks amazing. I don't know, Dan, do you have any questions?
No, I have 1,000 questions, but nothing that really is of course for this meeting. I'm super impressed of how far it goes, and super excited that it's already recognizing our mistakes, because that was also a big dream for it in that sense to work.
Really nice. All right, that's great. I believe, yeah, we went through all the presentations, so this is a good time to ask any questions for anyone who's here in the meeting and would like to get some more details, maybe on the models or maybe on any other aspect of the challenge. Feel free. Let's see, is there anything in chat? Oh, don't think so. All right, if there are no more questions, then yeah, then we can round up. I want to give Dan and Kai the opportunity to say some final words, and then yeah, we can round up the final presentations.
Well, first of all, thank you. I'm so sorry my webcam, or what is it, the camera is not working. It's a new laptop. But anyways, thank you so much for all of your effort that you've put into this. Dan and I have been talking about this for a while, and I never really thought that something like this would be able to exist and to help us out in such a way. So I'm really excited to start working with it and learn more about it, and hopefully continue to talk to all of you, because you know a lot more about all of this than we will ever do. So thank you so much for all of your work everywhere, wherever you are, and yeah, great job.
Thank you, Kai. Yeah, it was a pleasure working with you all. Always is, and it's really amazing to see how well the models perform, and with all the hard work you guys put in. So big thank you from all of us as well. You will receive a nice certificate in the end of this challenge from me, for which you will also receive peer review. But that said, that's some final details. But yeah, it's really heartwarming to see you guys all, besides your jobs, besides your studies, putting in so much effort in order to work on these challenges. So that's really cool. So thank you all, and I hope to see you in any future challenges.
Cool. Thanks, guys.
Thank you as well.
Thanks a lot for your effort, guys. Very,
Bye-bye, guys.
Thank you. Bye-bye.
Right.
See you.
Thanks,
Bye-bye.
everyone. Bye.
Thanks.